Hello and welcome to my Gifted and Talented Mentorship project showcase on magnetic induction as a novel solution for underwater communications. This project was done under the Gifted and Talented program at FBISD, as well as the University of Houston's Cullen College of Engineering. So some terminology before we get started. The data or bit rate is the amount of information that's processed over time. Attenuation is the reduction in amplitude or strength of a wave. As you can see in this diagram, the wave does decrease in strength over time. Propagation is simply the movement of a wave, and frequency is how often a wave completes a cycle in a given amount of time. And these terms will come up pretty frequently throughout my presentation. Underwater wireless communication has become an essential field of study as we continue to scour the depths of our ocean and expand our technologies to be more suitable to the underwater environment. Some common applications that we see today is oil and gas drilling, especially in Houston, aquatic life observation, as well as military use, especially with the Navy. But the problem is it's difficult to communicate underwater because of how hostile the environment is. Water is very salty and conductive. Water temperature is often very low, and water pressure is a lot more than air pressure. And water is often not very clear or turbid. And this essentially makes it hard for us to effectively communicate clear signals over long distances. Currently in the field, we have had some success, and there are three main forms of wireless communication: electromagnetic or EM, optical, and acoustics. EM communication is the most common type of land communication, and it uses EM waves to communicate, which are simply perpendicular electric and magnetic fields. The pros are it is stealthy, so it's hard to detect EM waves, which is beneficial for Navy use. And the waves do travel fairly quickly, which mitigates any sort of Doppler effect, meaning there won't be any sort of delays or distortions like with the receiver. And the cons are the water is naturally conductive, and since there are electric fields in the EM wave, it will alter some of the wave propagation. And we can bypass this by using low frequency waves, but those are not very capable of high data rates and often require bulky, expensive equipment. And this sort of communication also incurs heavy propagation loss because of the environment. Optical communication focuses on visible light, which is also a form of EM communication. And the pros are, once again, the waves do travel fairly quickly, which mitigates any sort of Doppler effect or any delays. There isn't much attenuation, and thus we have higher data rates, right? So we can actually convey more information in the same signal. And they work well over longer distances. But the cons are the attenuation is frequency dependent. As you can see in this graph, the lowest attenuation we see is with the blue-green waves, right? So we must only use blue-green light to communicate, which can be tricky and not very practical. As well as this sort of communication is very subject to the environment, right? So light can get easily absorbed, or if the water is not clear, then it won't be able to convey the light properly. And you must have a direct path of communication between the transmitter and receiver, which is often not viable. And this form of communication is also visible, so it's not very stealthy for Navy use. And lastly, we have acoustic communication, which employs sound waves and not EM waves. And this is the most common method that's used currently in the field. And the reason is there isn't much attenuation. While it is frequency dependent, as you can see in the graph, there's a lot more blue where there is less distance and a lower frequency, but there is a little red. But comparatively, this sort of communication has less attenuation, so it's easier to communicate. But the cons are these sound waves do propagate slowly, which means slower communication. But more importantly, it's an amplified Doppler effect. And what that means is there'll be multiple delayed and distorted signals that reach the receiver at the same time. And this can just cause us more work in terms of decoding the message that was initially being sent out. And it is audible, so it's not very stealthy. The current research that we're doing is on magnetic induction, or MI, as a form of wireless underwater communication. And this form of communication uses time-varying magnetic fields that are created by coils, which induce a magnetic flux. Right, so as you can see here, there's going to be a transceiver coil and a receiver coil, and these coils will create a magnetic field which allows for communication. The pros for this methodology is that the waves do travel fairly quickly, which, as I said before, prevents delays and mitigates the Doppler effect, which is to our benefit. The coils do prevent any sort of multi-path fading, which means there will be no energy lost from the coils. The MI waves are not affected by the medium as much as the previous methodologies, right? So there won't be like as much of a dependence on the environment or the water environment, and this sort of communication allows us to have a wider range of frequencies, right? So we can hear higher highs and lower lows, and we can hear over longer distances. And these coils are actually very cost efficient. Some of the coils that we use in our experiment can even be bought for under $1. The cons are there is low attenuation, but it's not based on frequency, which can actually help us out because we can easily code for it and decode the message. But the coils also must be aligned parallel for them to work effectively, as seen in this diagram. And this is a graphic that kind of shows the four methodologies that we discussed, as well as like the key characteristics for each. And you can see that MI is pretty much like the most efficient in terms of like as a whole a communication method. It is fairly fast and has like pretty big data rates, and it is very stealthy, which is good for military and navy use, over like the main form of communication and the main use of this sort of communication. And this picture shows us like how all these forms would be used simultaneously on a oil drilling platform. Okay, hardware for MI is those metal coils or loops, and essentially when we like run a current through these coils, they will generate a magnetic field, and then like any change in that magnetic field will create a flux, which allows them to communicate. So this like these coils are usually need to be parallel in order for it to work effectively. But actually, we've been able to mitigate the path loss as well as the need for this specific alignment by using omnidirectional coils, or a combination of 3 coils, right? So we have a combination of 3 different coils in the X, Y, and Z direction, and this allows us to create fields in the X, Y, and Z direction. And that just allows us to communicate more freely and more flexibly, so we don't always have to have like those coils being exactly parallel. And this is even beneficial for vehicles that move underwater. So these coils can communicate like while the vehicle is moving. The software for MI, as well as most methods of communication, is signal processing. Signal processing itself is any form of analyzing or modifying a signal, which is just any sort of recorded data or information over time. Digital signal processing is a form of signal processing that works on the quantized theory, so everything is in terms of integer numbers and whole number steps. But the analog signal processing is based on the continuum theory, so everything is very continuous and has like a continuous flow of space and time that it uses to record this data. And the reason we have both these like different types of processing is because processing itself is best done digitally. Propagation is best done in analog. So like these communication systems, I'm sure like how these different worlds, if you will, interact with each other. And the best way for us to effectively go back and forth between these two worlds is through something called the sampling theory, which is a constructed way to move between the analog and digital signals. And essentially, what we're doing is we're linking the speed that we need to take samples at to the maximum frequency in the spectrum. Right, so if we take samples like at a specific a frequency, which is a maximum frequency, and link the speed to it, we can actually like form a digital wave that is like fairly representative of the analog wave. And this shows like how we can do that through like a bit of calculus. Some examples through code that I was able to do through a software called MATLAB. So we started off pretty simple, with by graphing a cosine function, and this is fairly simple. It just goes from 0 to 2 pi, and it's a cosine function. But you can see how we actually have intervals of pi over 12. So it's so it makes the cosine function like fairly like representative of the actual cosine function. But if we had like larger intervals, then it wouldn't be as effective. And we're also able to generate a random bit stream, which is a bit more like implicative of the communication that we're going to do. And these are just a 10 random binary bits from 0 or 1. And then that leads us to a bit more complicated code, which is called a Bpsk modulation, or a binary phase shift key modulation. And essentially what's happening here is we start off with a carrier wave, or just a simple sine wave, which is an analog. And then we convert it to a square wave, which is in digital. And then we actually have to convert it back to analog, because like the beginning is more of the propagation, and then when it's processed, it's best to be done in digitally, and then it goes back to propagation. But when we convert it back, there is actually a 180-degree phase shift every time this square wave goes from 1 to -1. Right, and that's where like the phase shift comes in, because we have like that 180-degree phase shift. I'm just like to make the propagation processing a bit easier for us. Okay, the experiment that we did, I wasn't able to do, but my mentor was able to do in the lab, is basically test this MI theory and communication on a small scale lab setting. So we do have the two coils that are placed around 3 feet apart, and each are about 9 inches in diameter, and they're hooked up to the signal processors, which is the USRP N210, and that handles like most of the processing like for the signals, like going back and forth between the two, digital and analog. And these computers over here will like transmit the image and then receive the image, and the idea is we transmit an image, and then we try to communicate this through the water using the two coils, and then receive it on the other laptop and see like how effective was the communication. And this picture in the corner is like a prototype for the omnidirectional loop that I was talking about before. And the results were pretty astounding. We were able to convey or communicate a picture of a cougar for U of H, and the transmitted image is very clear, and the received image is actually pretty clear for magnetic induction, for it to being in like a very experimental phase. The image is actually pretty clear. There are some blurry, some like spots of blurriness around the image, and the biggest, I guess, distortion is the line down the middle. So like where it's like some pixels weren't able to be transmitted effectively, and this can be due to some sort of eddy current in the water, or even like some sort of a mistake in the electrical signals or the processing that could have caused this line. But the rest of the image is fairly clear, which shows a great promise for MI as a form of underwater communication. And these tables show us like some of the path loss and attenuation characteristics of MI graphed with distance and frequency. And this was done by my mentor's professors, and which has a more focus on ROVs, or remotely operated vehicles. Okay, so in the future, the use of MI is still in its developmental phases, but many companies and researchers are beginning to see like how effective and versatile it truly is. Freelink is a company that actually uses MI for pacemakers and for walkie-talkies, and they find it very effective. And U of H has become like a leader in sorts of developing and experimenting with MI. They do a lot of experiments with MI like on remotely operated vehicles, so vehicles that you can like control with the remote control. And I truly believe that MI will become the premier form of underwater communication, simply because we can communicate over longer distances more effectively with clearer signals. And like once we like fully implement the use of this omnidirectional coil, it's actually very effective for us to be communicating like while submarines are moving. and that sort of thing. In the future as well, I believe MI will be more used in space as well. Like it will be used to communicate like in space as well as to even like see like underwater in space. So I know like trying to use MI currently in Europa, one of the moons of Jupiter, to see under the ice. Right, so like MI will become a very prevalent form of communication, both underwater, on Earth, and in space. Me personally, through the knowledge that I've gained in this field as well as in my own interest, I want to be able to combine these and work on devising like a more effective means of communication and improving upon like MI itself. So similar to how we were able to improve upon the coils and make an omnidirectional coil, I want to improve upon what we have right now and make sure that MI can become a very reliable. An example of that can be like working on the signal processing and making sure processing is done more effectively and more efficiently. I also believe that by the time I'm able to work on MI in the lab, it will be used vastly across space. Right, so like on my role, I will be able to use MI in space more effectively, maybe account for like the magnetic field of the Earth and other celestial bodies, and being able to explore like other icy regions of other planets as well. And lastly, I want to thank my mentor, Mr. Chen Pai Huang, as well as Miss Bryant, our GT mentorship sponsor, for doing all their hard work. Thank you both for this wonderful opportunity, and thank you for listening to my presentation. And these are the references for my presentation.